Okay, so let's try a couple of examples with Green's theorem. So I'd like you to take this vector field F. I want you to find the circulation counterclockwise around this triangle. And I want you to try it two different ways because we've now learned two different methods. And actually, before you work on this problem, I want to just point out the different ways that this same question may be worded. You may see us say, okay, find F dot dr, or we may say find F dot t ds around this curve C, and because it's a closed curve, we'd put closed things like this. And the last way you may see it is in the form where we've actually started to take the dot product a little bit. If we called, this is my I component, right? So I would have 1/2 y, that's the I component, and then dx. That's one way of thinking of it, where what I've done is expanded out. So if you recall, this is the same as p dx plus q dy, where this is the I component and this is the j component. And so in this case, you might just get this integral asking you just to do 1/2 y dx, but it's really saying, oh, you can imagine this is just the I component of your vector field, and we're asking you to define work or circulation or flow. So go ahead, put this on pause. Remember, you're going to learn math much better by actually doing it yourself than just waiting and watching. So put it on pause, challenge yourself to see if you can find the circulation two different ways. Okay, first way, I would recommend starting by trying Green's theorem. It's usually going to be faster if you have a closed curve, as long as it applies, as long as the conditions apply. So I need the components of this vector field to be continuous and to have continuous partial derivatives, which they do. And then what I've sketched here is the vector field in gray. You can see it only has an I component. It's getting longer the further up you go. So if you could imagine it as water, the water is moving faster the further up we are. And then we're going to calculate, imagine putting little tiny paddle wheels. That's kind of what the red's supposed to be inside here. And we're calculating what their rotation would be, what the speed of their rotation would be at a given point inside here. How quickly are they circulating? And we can see that because the curl is -1/2 k, this is telling us that we would expect these to rotate clockwise because it's a negative here. And it's rotating around the k-axis according to the right-hand rule. So that's why it's going clockwise. And then the scalar component, -1/2, is giving us a sense of the speed at which it's rotating. And so what we can do is now think of that, this -1/2, as being like a circulation density. So this is going to be like our circulation per unit area on the inside, and we can add that up everywhere on the inside, and that should give us the overall circulation around the boundary. And so in fact, that's what we get here. Our overall circulation is -3/2, which you can see that we have more of the vector field that is going against the region or the direction that I'm moving. Like I'm moving along the curve right here in the direction of the pink vectors, but my vector field is moving away from that. So that's why I'm getting more of a negative contribution. I don't have this vector field really flowing around this triangle in a triangular fashion. It's going more around, it's actually going more clockwise than counterclockwise. And we can also see this by doing this just each individual line integral. And then I think you might be able to see what I'm implying as well. So let's go to this. The second option is to use line integrals and look along each side of the curve to what extent the vector field is flowing in the direction of that curve. So we can see along C1, first of all, my vector field doesn't even exist along C1 because y is 0. So I don't have any flow along here. And then along C2, I need to parameterize. So one way I could parameterize starting at the point 3, 0, ending at 0, 2 is to parameterize like this. And then I find my velocity and I take the dot product between my vector field and the velocity to get this -3/2. And then notice there's no contribution coming from this side C3 because the vector field is totally perpendicular. So it's not at all moving in the direction of the curve here. So I'm really only getting contributions to the circulation along this component of the boundary, and we can see it's going against the direction of the flow for the most part, which is why we're getting this -3/2. Okay, let's try another one. So again, put this back on pause and compute this one 2 different ways. Now we're doing the work around the circle of radius 2 centered at the origin. Okay, so option 1, we can compute the line integral directly, and I didn't actually have us do that in a warm-up, but I can show you that on the next page. Option 2 is what I would start with, actually, is to use greens. And so you notice in this case that our curl is going to be this vector -3 x squared plus y squared k hat. So therefore the k component is just -3 x squared plus y squared. And so if I'd like to know what's happening around the boundary, I can integrate this k component of the curl. Because this region on the interior is a circle, it's screaming to do a coordinate change. So we switch to polar, and then we end up getting -24 pi. Okay, and then here is option 1, which would be to actually do it the long way by parametrizing. And in this case, I'm going to parametrize the circle. The easiest way to parametrize that is just to use cosines and sines. And then I'm literally just plugging in, rewritten my vector field in terms of my parameterization, which is right here. And then I have my v, and my Jacobian cancels with the speed here, so I just have v dt, and I expand it out. And it gets to be a little messy because it's got these 4th degree or sine and cosine to the 4th power, but we know how to do this from Calc 2. And so we just continue plugging and chugging along, plugging and chugging along. And the point is we're going to get the exact same answer that we did before, but this was a lot more work. And so thank goodness for Green's theorem circulation form when it applies. And that's usually what I'll try first, because oftentimes it can save us from a lot of extra work like this.